Okay, we're going to talk about Unit 7.6, the Fundamental Theorem of Calculus, Part B. So let's do an exploratory problem to begin with. Let's do the problem, the derivative of the definite integral from 1 to x of t squared dt. Well, how do we do this? Let's break it up step by step. Let's begin with our parentheses. So step 1, let's go ahead and integrate our function. So we're going to evaluate our definite integral first. So the integral of t squared is just t cubed over 3. So we'll evaluate that from 1 to x. There it is. We'll plug in our x because that's our fundamental theorem of calculus that we already learned, f of b minus f of a. So f of x minus f of 1. So we plug that in and we get, when we plug in x for our t cubed, we just get x cubed over 3. When we plug in 1, we get 1 cubed over 3. So here's f of b minus f of a. And that's going to just equal x cubed over 3 minus 1/3. Okay, but we're not quite done. We've only dealt with this part of it, but we haven't dealt with the first part. So what does d dx mean? It means take the derivative. So that's what we're going to do for step 2. Let's go ahead and take the derivative of what we just figured out, this x cubed over 3 minus 1/3. Well, what do we know is going to happen to the right-hand half? The derivative of any constant value is just going to be 0. So this part just disappears. Well, what's the derivative of x cubed? 3x squared, so that becomes 3x squared over 3. My 3's cancel out, and I'm simply left with x squared. You can see that over here, x squared minus 0 is just x squared. Okay, let's do one more exploratory problem. Let's take the derivative of the definite integral from 1 to x of 5 over t to the 6th dt. So first things first, let's do the integral. So we'll evaluate the definite integral. So let's go ahead and do that. First of all, this 5 can come out. We can just leave that. That means it'll just come down. And this t to the 6th on bottom is going to turn into, it'll actually be 5 times the definite integral from 1 to x of t to the negative 6 dt. Well, now we can see we can apply our power rule right there. T to the negative 6 just becomes t to the negative 5 over 5. If we integrate it, I bring my 5 back, and we get 5 over 5t to the negative 5th. And of course, from there we can simplify. So we get this first answer, and from there we can simplify. We can cross out our 5's. We still have that negative, and I have t to the negative 5th on top, so we don't like negative exponents, so we're just going to bring it back to the bottom, and that's going to become negative 1 over t to the 5th. Evaluated from 1 to x. Here's our other fundamental theorem of calculus. This is f of b minus f of a. So here's our b. I plugged in my x. Here's our a. I plugged in my 1, and we're left with negative 1 over x to the 5th minus negative 1 over 1, so plus 1. But we're not done, so let's do step 2. Let's actually take that derivative. When we take that derivative, again, the constant value on the right disappears because the derivative constant is 0. And we're just going to take the derivative of this part right here. Again, we may want to rewrite this. This is actually negative x to the negative 5th. And now we can take the derivative of this. We bring it down, etc., etc. And we get our derivative would actually be 5 over x to the 6th. I know you can't quite see it here, but it is 5 over x to the 6th is what we're left with. So what does this mean? We did these 2 exploratory problems. What does this mean for us? So let's look at that. Let's evaluate it. Here was question number 1. I just rewrote it so you have the answer. Here's question number 2. And what do you see? Do you notice any patterns develop? What do you notice? Anything at all? Well, I notice that this looks awfully similar to this. The only difference is I plugged in the variable I had, which was x. This looks awfully similar to this. The only difference is I plugged in the variable we were replacing. So that is the fundamental theorem of calculus, the other half of it that we're going to learn. It must be continuous. You have to have a derivative at any point. So remember, the big letter F typically stands for my antiderivative, my integral. So my big letter F is equal to this definite integral. So if we know that, then the derivative of the integral, which is what we did in the last 2 problems, right? The derivative of the integral is equal to the derivative of this integral, that's what we did, must be equal to the original function with respect to whatever we got going on here, okay? At this point, it's as simple as replacing. We will see in a little bit, there's a tiny bit of the word gets a little bit more complicated, and we'll do those problems. So, problem number 1. Now, when I did our exploratory problems, I did step 1, we integrated the definite integral and evaluated it, and then step 2, we took the derivative. But we saw that something happened. We were able to just simply replace. So let's talk about some conditions where that's okay. So condition number 1, is my A a constant? Condition number 2, is B simply just X? Then we can just rewrite as X. So let's double check our conditions here. Is A a constant? A is 4, yes. Is B just X? It sure is. So then we can go ahead and do step 3. We can rewrite it as with our letter X. So instead of the cube root of 1 minus t plus t squared, it's going to become, with my x's, the cube root of 1 minus x plus x squared. And that's just the answer. We have no more derivative, no more integral, because those are going to cancel each other out. So you're just left with the cube root of 1 minus x plus x squared. It's as simple as this. When you have A as a constant and B as x, you can just rewrite. So let's double check this one. Is A a constant? Yes. Is B just x? Yes. So we're good to go. We can just replace. So this is going to become the sine of x over x. That's simple. Next one, is A a constant? Yes. Is B just x? Yes. So I'm going to replace e to the negative x squared. Every time I see a t, I replace it with whatever I've got, which is my x. All right, here's another one. Is A a constant? Yes. Is B just x? Ooh, here we have our other condition. So you ask yourself, is A a constant? And is B something to replace? Then what I'm going to do is I'm still going to replace. That's what it's going to be in this first half. We're still going to replace whatever B is for our variables in our function. But then we're going to multiply by the derivative of whatever that B value was. So we do our double checklist with this. Is A a constant? Yes. Is B something besides x that we do need to replace and is not a constant? Then we can use this. We go ahead and replace just exactly as we've been doing before, but now we're going to multiply by the derivative of whatever B is. So let's apply that to this equation right here. Whoa. Okay, let's apply that to this equation right here. So A is a constant, B is not x, but it is something I can replace. So let's go ahead and do the first half. 1 over, instead of t, I'm going to replace it with cosine x times, and here's that part that I said, what do we have to put here? The derivative of b. What's the derivative of b? Well, b is cosine, so the derivative of cosine is negative sine x. I'm going to multiply by negative sine x. At this point, I'm technically done. However, if this were a multiple choice question, this may not be the form that we would see. We have to reach back into our heads, into pre-cal, into those trig identities. This is a quotient identity from pre-cal. And what is, anybody know? Okay, put it like this, maybe we can recognize it. So we see negative sine x over cosine x. Maybe we recognize that quotient identity. This is actually equal to negative tangent x. That one we should know. Okay, if I double check my work, ta-da! Awesome. Okay, let's do our next one. So in your packet, it may look a little different, but I want you to see what this says. So it says if some function g of x is equal to the definite integral, then I want you to find g prime. So let's read that out to ourselves. What is g prime? What does prime mean? Does it mean take the derivative? Cool. So we are taking the derivative of g of x. What is g of x again? Is g of x my definite integral? So I'm taking the derivative of a definite integral, especially with some value x up there, but I'm taking the derivative of a definite integral, what does the fundamental theorem of calculus tell me? Is that definite integral and the derivative going to cancel out? Yes, they are, and I'm just going to be left with my function, but with respect to the correct variable, so we have to take care of that. So let's go through our checklist. Is A a constant? Yes. Is B just X? Yes, so we can stop right there. We can just replace. Okay? So I'm going to replace, so it becomes E to the tan, and instead of X, T, I'm going to put X right there, and that's it. My integral canceled out because my derivative was outside of it. Cool, simple as that. So the whole purpose of this slide was simply to show you a different form that they could have written it. You would see this form on tests, just like you would see the other form on tests. So, all right, let's run through our checklist. Is A a constant? Yes. Is B just X? No. But is it something I can replace? Yes. So what are we going to use? We're going to use our second condition, and we're going to put our replacement multiplied by the derivative of our B. So what are we replacing? So this is going to become cosine. Every time I see T, I'm going to put X cubed. So X cubed, but I cannot forget this squared right here. So X cubed squared times the derivative of B. My B is X cubed, so the derivative of that is just 3X squared. I can rewrite this, simplify X cubed squared. So if an exponent raised to an exponent, I'm going to multiply those numbers. So this becomes cosine of X to the 6th. This value comes to the front because that is the correct notation, and there is my answer. Double check my work. Boom. Awesome. Let's do another problem. All right, let's run through that checklist. First of all, let's read it. We're finding G prime, so we're finding the derivative of G. G is an integral, so the derivative of an integral is fundamental theorem of calculus right there. So we're going to run through our checklist. A. Is A a constant? Whoa, A is not a constant. Okay, well, let's check. Is B a constant? No, so they're not just backwards. Something else is happening. I got multiple letters here. So let's actually just break this down for a second. Do we agree that our interval goes from X to X squared? Okay, that's what's set up by my definite integral, my parameters from A to B. That's our interval. So what we're going to do is the property called additivity from integrals. You learned this in Unit 6. If you didn't learn it, now's your opportunity to go back and double check those 5 properties I gave you. So we can put some value in between and split this up. So we're going to put some constant number here. What's the easiest constant number we like to use? 0. Technically, any constant value can go here. I can put any letter C because we know the derivative of a constant is just going to be 0. But we're going to go ahead and let it be 0. So let's do our additivity property and let's split them up. Additivity. And what that means is I now have a new interval right here, and I have a new interval right here. So let's rewrite that. So that becomes the integral from X to 0 of my original function, 1 over 2t dt, plus additivity, plus, let's not use the wrong operator, the integral now from 0 to x squared of 1 over 2t dt. Okay? Well, now we're mostly set up, so let's reevaluate these integrals. We are still taking the derivative of this whole thing. We are still doing that. That hasn't disappeared. So we're going to apply our fundamental theorem of calculus. Start with this one. This one's a little easier. So is A a constant? Yes. Is B just X? No. But is B something I can replace? Yes. So we know what we're going to do with this half. We're going to replace and multiply by the derivative of B. But what happens over here? Okay? Is A a constant? No. Is B just X? No. But what happened here? Are they just reversed? Oh, cool. So if they're just reversed, what I can do is if I want to flip them, if I want to turn this into 0 and this into X, if I want to flip them, I got to change something out here. I have to change the sign. It's currently positive, so we're going to make it negative. If it were negative, we would make it positive. So now that it's like this, am I ready to go ahead and do our replacements? I sure am, so let's go ahead and do that. So this is going to become negative, can't forget my negative, 1 over 2x plus, and then this section right here, 1 over 2x squared times the derivative of b. So the derivative of x squared is just 2x, so it becomes 2x. I'm going to do the rest up here since I'm running out of room. Okay, so this becomes negative 1 over 2x plus, and here I'm going to do 2 over 2x. What I did is I got rid of one of the x's. I had one x up top and two x's on bottom, so I got rid of one of the x's. And some of you might ask, well, Miss Jack, why didn't you get rid of these 2's right here? Well, okay, sure, but what's happening right now? Do I have common denominators? I do. So since we're already set up for that common denominator, I might as well just put them together. If we weren't, you know, like I tell you guys, you just leave it in its most simplified form that you see, and that's okay. So technically, this answer is correct. Technically, if I had left x and this had been x squared, that answer is all correct. They're all correct answers. But let's go ahead and simplify this. 2 minus 1 gives me 1 over 2x. Well, actually, what's going on there? You know, is there a relationship between what's happening? So if I went from x to x squared, we got the same answer that we would have gotten from going from 0 to x. So it's kind of interesting to see how that happens. There's our answer. All right, here, let's run through our checklist. We are taking the derivative of this. That's what your sheet of paper tells you. So we're taking the derivative. So if I'm taking the derivative of an integral, I am still doing the fundamental theorem of calculus. So I can just look through my checklist. Is a constant? Yes. Is b just x? No. But is b something I can replace? Yes. So I'm going to replace and multiply it by the derivative of b. So let's go ahead and replace. This becomes, my s becomes the square root of x. But I can't forget the squared times the derivative of x, square root of x. So the square root of x is the same as saying x to the 1/2. So if I bring that forward and subtract 1, then I get 1/2 x to the negative 1/2. So this becomes 1/2 to the negative 1/2, so square root of x. Okay? Not 100% done. If I square a square root, what happens? Well, those just cancel out, so this becomes x over x plus 1 times 1 over 2 square roots of x. I'm going to double check that answer. There it is. We did it correctly. All right, let's run through our checklist. Is a constant? Yes. Is b just x? No. Is b something I can replace? Yes. So let's go ahead and do condition 2, and let's do our first replacement. So I see a t, so it's going to become cosine x. And then my cosine just comes down again, but I see another t, so we're going to put our cosine x there. But my t was actually cubed, so we're going to cube that cosine x. I want to make sure, very carefully, I want to remind you guys about trig notation. I want to make sure that my t was cubed, and since I'm replacing t with cosine x, so my cosine has to be cubed. I want to make sure we don't accidentally cube our x. If I put the cube right here, it would have been x cubed, but I put the cube right here attached to my trig, so that means cosine is cubed. All right, but we're not done. We have to multiply by the derivative of our b. Our b is cosine x, so we know that. The derivative is sine x. So if I rewrite this, I'm going to bring this to the front, make it easier on me. So it becomes negative sine x cosine x times cosine of cosine cubed x. Okay? We can double check, see what we got. Awesome. Same exact answer. All right, let's double check this one. Is a constant? No. Is b just x? No. Is b something replaceable? No. What is b? B is my constant. What is a? Something I can replace. Okay, are these just switched? Yeah, so let's rewrite our original integral. So if I rewrite our original integral with these values reversed, our a and our b, if I switch these, what did I have to do out here? I had to change the sign, so let's make it negative. Now am I ready to replace? Ooh. Yes. Now I'm ready to replace. So if I'm taking the derivative of this integral, which is what your packet tells you to do, taking the derivative of this integral, now I'm ready. A is a constant, B is an x, but B is something replaceable, so let's go ahead and do that. This becomes sine, I see t of tangent x, but t was to the fourth, so my tangent is also to the fourth, times the derivative of tan x, which is just secant squared x. Can't forget my negative. Bring that negative down, and there's our answer. We could rewrite it in a more visually clarified form. So negative secant squared x times the sine of tan to the fourth. All right, here's another problem. So we're looking at example 3a now, and the first two are kind of just a review. They're not really the fundamental theorem of calculus, because what are we given? We're told that capital letter F is equal to our definite integral. We know that, right? Capital letters tend to be our integral. So when it says find f of x, what are we doing? We're just evaluating the integral. It's as simple as that. So let's evaluate that integral. This is not the fundamental theorem of calculus that we're learning today. This is the fundamental theorem of calculus that we learned last time, f of b minus f of a. So we're going to do our f of b minus our f of a, and that's going to become f of x minus f of 2. And let's integrate that real quick. The integral of 1/3 t squared is equal to 1/3 times the integral of t to the negative 2, which is equal to 1/3 t to the negative 1 over negative 1. So this becomes negative 1 over 3t. Okay, so we'll plug that in. Negative 1 over 3 instead of t, it becomes x minus a negative, so plus 1 over 3 times 2. So this becomes negative 1/3x plus 1/6. Okay. This is the same as this. We just extrapolated that 1/3. So if you wanted to see that, this becomes, I can pull out negative 1/3 here, so it becomes pull out positive 1/3. So I'm left with negative 1 over x plus, if I pull out that 3, that becomes plus 1/2. So that's where that comes from. We just switch these values. The same answer. Okay. The only difference between question 3a and question 3b is what? That 2. So does that mean I'm just plugging in? So instead of, so here my f of b minus my f of a is actually going to be f of 2 minus f of 2. Well, just looking at that fundamental theorem, what do you think my answer is going to be? We think it's going to be 0, right? But let's double check. Let's just make sure. If we plug in 2 where we had x before, well, what's going to happen right here? These are going to cancel out, and I'm going to be left with 0. All right, here's where we're cracking at the new fundamental theorem, where we take the derivative of that integral. Or isn't that what we're doing? The derivative of an integral. So we can just replace. Let's go through our checklist. Is a constant? Yes. Is b just x? Yes. So we can just replace. So it's going to, instead of be 1 over 3t squared, it's going to be 1 over 3x squared, right? Ooh, I went too fast for that one. If you need to see it, 1 over 3x squared. And again, the only difference between question C and D is that 2. So instead of x, we're actually going to do our, we're going to plug in our 2. Okay, here, this time though, our theorem is going to be a little different. So what happens when we plug in that 2? We get 1/12. Okay, before we move on to example 4, I want to do a little bit of review of the concepts we learned in unit 4 and 5 back in December, where we did f prime and f double prime. So we're going to fill out this little chart. I know it's not in your packet. If you want, you can write something down or put it on a separate piece of paper, however you want to do it. Now, in the past, we've learned it as f prime, f double prime. However, we see f a lot in questions, right? So let's go ahead and rewrite it as g, g prime, and g double prime. We'll just live in that world for a second. So let's fill out this chart. The function one should be easy. That's algebra. That's not even calculus. So when g equals 0, what do we call those? Well, the zeros is 1, but what's the other word? Root. This would be our roots. when g is physically positive, then that means I'm above the x-axis. And of course, when g is negative, it means I'm below the x-axis. And let's make a clarifying statement right here. When I say positive and negative, I am not referring to the slope. I am referring to its actual function value. When its actual function values are positive, then it must be above the x-axis. We're not talking about slope here, okay? All right, what about g prime? When g prime is 0, what did we call those? They started with a c. Okay, these were our critical values. Okay, this was what we associated with extrema. Again, we didn't know for sure it was extrema. You have to test it, but we do associate it with extrema. When g prime is positive, when g prime, the graph of g prime, is above the x-axis, what does it mean for our function? It means our function must be increasing. And so if g prime is negative, then our function must be decreasing, right? Okay. G double prime, when it equals 0, it would equal this little acronym, I guess, but 3 little letters, POI, points of inflection. And what are points of inflection? They are changes in concavity. Again, we have to test this to know if it's a true change in concavity, but it's a possible point of inflection when it equals 0. Well, what happens if the graph of G double prime is positive or above the x-axis? This tells us G is concave up. It's smiling. So that if it's negative, then G must be concave down. So we see this relationship. We knew all of this. This hopefully felt like review. If it didn't, you may need to go back and look at Unit 4 and 5. But this is just that review concept. But let's relate it to what we're talking about today. Okay? So let's put in our values here. Okay? So let's talk about our function, our integral, and our derivative. So I'm going to put my function smack dab in the middle. Because what happens when we knock it down a peg? That's deriving it, right? X squared becomes 2x. I knock that exponent down. I bring my highest power down. Well, what happens when I integrate? Do I bring my highest power up? Yes. So there's our integral, our function, and our derivative. Well, just like we have a relationship between g prime, and g double prime with our first derivative test and our second derivative test, there is also a relationship here between the integral, the function, and the derivative. We can actually relate those. So if I have these 3 things, if I know I'm dealing with 3 parts, which is what we've been dealing with all day today. We've had a function, we've taken the derivative of the integral, so we've dealt with all 3 parts. If we're dealing with all 3 parts, we can see these as these relationships up here. I can also shift them over and see them as other relationships, you know? If I'm just looking at f, or the integral and its function, I can look at it as a relationship between g and g prime, or the relationship between g prime and g double prime. It just depends on what information we're given. So, first things first, let's just figure out what we're given and what's important in this information. So we are given the graph of f, that's what that is. But that's not the equation we were given. The equation we're given is h of x. And what is h of x? It's equal to my integral. So h is actually my integral. So let's relate this in terms of our g prime, and g double prime. So, again, if this is our relationship, f prime, integral, function, and derivative, what did we relate it to? G prime, and g double prime. So what is our function related to currently in this state? G. And what is our function? Our integral is g. What is our function related to? G prime. So let's go ahead, and we're going to just declare that right now. H of x is actually our g, and this graph right here is actually our g prime. So this is going to help us understand what we're looking at. We're not looking at the graph of a function. Yes, it's the function in the equation, but we're not looking at a graph of a function. We're looking actually at the graph of the first derivative test. So what's that going to tell us? Well, it's going to tell us all the information that we would know from a first derivative, which is why we made that little table. Wasn't a truly conclusive table, but that's okay. So here, again, we can look at this and say, okay, well, this isn't just h, this is actually our g. this is our G prime, and this is our G double prime. Can't we look at it like that? Well, that's pretty easy. We can also look at it like, what is H? Okay, H is my integral. This is my integral. What is H prime? That's the original function. What is H double prime? That's the derivative. Okay, that's going to help me understand this question. So we can figure out this one, we can figure out this one, this one, this one. This one's pretty easy. I look straight at what my function is doing. Where do I know I've got my function? The graph. So I know I can figure out what that's doing. This one's pretty easy. What do we know about slope? Sorry, I gave that answer. What do we know about derivatives? My derivative is my slope. So this is actually the slope. And what's the integral? My definite integral is my area, right? So this is just area. So that first one's pretty easy. From 0 to 2, what shape do I create? A triangle. Triangle with base 2 and height of 1 tells me my answer is 2 divided by 2, which is just 1. Okay. For my second one, h prime of 2, I have to look at what my function is doing. Well, what is my function doing at 2? My function at 2 equals 0. So that's pretty easy right there. And finally, I can look at what is my slope at this point. Well, at 2, this is a linear line. That should be easy. I can figure out that slope. Down 1 over 2, down 1 over 2, down 1 over 2, right? So my slope is -1/2. Boom, that's simple. The hardest part about this question was reading and understanding what it's asking us. Let's look at our next question. For what values of x? So we're searching for x. X equals what? In the open interval from -2 to 10. So that means our entire graph that we see is h increasing. So again, we know that h is actually, I don't like that pen. H is actually g, and this is g prime. So what do we know about the relationship between g and g prime and increasing? Well, g prime is going to tell us increasing, decreasing. That's calculus. But what does g prime have to be doing for g to be increasing? We can go back to that little graph. I see g increasing. What was it doing? It was positive. So where am I positive on this graph? What does that mean? Where am I above the x-axis? So from -2 to +2, and from 8 to 10. So from -2 to 2 and from 8 to 10. They didn't just finish there though, I needed a justification. So h must be increasing on these intervals because f is greater than 0. And I want to make a note here. Why did we use h and f? Because we are justifying with what we are given. Okay? Our next question says, find the x-coordinate of each point of inflection of h. And again, so we know this is actually g, and this is g prime. Well, in our table, in our little chart that we filled out earlier, we didn't talk about how points of inflection are related to g prime. So let's talk about it really quick. We know that points of inflection are where g double prime equals 0. But what do we know a point of inflection is? It's a change in concavity. How do I see a change in concavity on g prime? Well, if it's g prime, then g prime's slope changes from positive to negative or from negative to positive. So g prime's increasing goes to decreasing, or decreasing goes to increasing. If this were g double prime, it would go from above the x-axis to below. And if this were my actual function, I could actually see where concavity changed. Okay, so where do we see this graph of g prime? Where do we see g prime either changing slope's sign or going from increasing to decreasing, decreasing to increasing? It's your decision how you want to see that. Well, right here, I have a positive slope or increasing going to a negative slope or decreasing, so that could be a point of inflection. And here I go from a negative slope or decreasing interval to an increasing interval or positive slope. So there's a point of inflection right there at 0 and at 6. So that's good. We just need our justification statement. So H, what we're given, right? H would have points of inflection at these two values because F, even though we know it is G prime, F is doing what? What did we just talk about? F's slope is either changing sign or F is going from increasing to decreasing or decreasing to increasing. So there it is. At 0, x is equal to 0 and 6, there must be POI at these x values because F goes from increasing to decreasing and vice versa. Now we're talking about what values of x in the open interval, so this whole graph, is h concave down. So again, this isn't our h, this is g, this is g prime. So what's that relationship? Where do we know that this is concave down? So we were either looking for g double prime to equal 0. We don't have g double prime. So we're going to use what we just talked about in the last slide. How do we know the relationship between g prime and concavity? We know we're looking at either slope or increasing, decreasing. That's what we know we're looking for. So what do you think we're looking for with concave down? What kind of slope, or which of these two? Yeah, we're looking for a negative slope or a decreasing interval. So where do we see a negative slope, which is a decreasing interval? Okay, we see it from 0 to 6, but what is our justification? H must be concave down. Again, with what we're given, H must be concave down on the interval blah, 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 because F, what is F doing? F has a negative slope or F is decreasing. So, boom. There's our justification statement. Now we're looking for where H attains a relative maximum. So when would G attain a relative maximum? This is G prime. What do we know a relative max is? Well, a relative max is where G prime equals 0. Those are our critical numbers. But this isn't actually true. I lied to you. I'm sorry. Relative max, not necessarily true. What I'm talking about is our extrema. Critical values, G prime equals 0. How do we know if it's a max, though? We have to make that clarification. We have to know. If it's a max, it would look like this, right? A max versus a min, which would look down here. So to create a hill instead of a valley, what did I do? What kind of slope is this? Positive slope, so I'm going from increasing to decreasing, not decreasing to increasing. So let's look at where our critical values are. So I have a critical value right here, and I have a critical value right here. Which of these is our relative max? Well, I'm going from above the x-axis to below the x-axis. So that's the relationship here. Above to below, and this is below to above. So this is above to below, this is below to above. So we're actually going to use this one right here at 2. So x equals 2, there must be a relative maximum because F goes from positive to negative. Now we're going to go back into our brains from Unit 2 and we'll talk about that average rate of change. So what do we know is the formula for average rate of change? Yes, it's f of b minus f of a all over b minus a. So let's plug that in with our h. So this becomes h of, here's my b, 10, minus h of, here's my a, negative 2, all over b minus a. So b minus negative 2 gives me b plus 2. So let's figure those out really quick. Let's figure out what h of 10 would be, and let's figure out what h of negative 2 would be. Well, how do I figure those out? Well, we saw that in question 4a. How did we figure out what h of 2 was? What did we use? Not h prime of 2, not h double prime of 2, h of 2. We used the integral, and the integral is just my area. So let's figure out area under the curve. 10, well, what's my starting value? 0, that's given to us. So from 0 to 10, let's figure out our shapes. There's one, there's another, there's another. We know this one, we solved this one. This is 1. I'll tell you this right here, base of 6, height of 2. My area is 6, not quite. My area here is negative 6. And then this final area is 4 and 4, so, 2 and 2, so 2. So if I add these up, 1 plus -6 plus 2 gives me -3. My final one is h of -2, so I'm going from 0 to -2. Okay, so this is still an area of 1. However, where am I going? Are we sure it's +1? No, we're not, because we're going backwards, right? From 0 to -2, I went backwards, so this is actually -1. So I fill all that in, and I get -3 minus -1 gives me +1 over 12 equals -2 over 12, which equals -1/6. And that's our rate of change, average rate of change, sorry. So I want to double check that work. Boom, -1/6, yay. Okay, now we're going to do question 4G. Woo, that is a lot more words than we've seen before, so let's break it down. We're looking for how many values of C, so C equals, that's what we're searching for, from the interval 0 to 3, so I'm only looking from 0 to 3. I don't need any other information. Is H prime of C? Whoa, H prime of C. What is that? What do we know H prime of C is? We're taking the derivative of our integral. So the derivative integral, the fundamental theorem of calculus tells me is equal to, it's not equal to my derivative, it's not equal to my integral, it's now equal to my function. They cancel out. So this is just saying, where is my function equal to the average rate we found in the previous one? So we already know that equals to -1/6. We figured that out in the last slide. All we have to figure out is what's on this side. My function is equal to, well, what's my function? Where do I get that? This f of t, where do I get that information? Ta-da, our graph, right? From 0 to 3, yes, this whole function has 3 piecewise lines, but from 0 to 3, we only have 1 line to worry about. In fact, it's the same line we've been looking at. That has a slope of -1/2. We figured that out in the very first question in example 4. And it has a y-intercept of 1, so I know the equation on this side. -1/2x plus 1. This is a reminder. Algebra doesn't disappear. Yeah, you didn't really need the algebra to solve the rest of the questions, but you needed it for this one. So every now and then you will have a little bit of algebraic exploration. So if I solve for x, it's pretty easy, right? If I subtract 1, that's the same as saying subtract 6. And then I multiply this by -2. So I'm going to multiply my -7/6 by -2, which gives me, my negatives cancel, this becomes 3, +7/3. That's what my x would equal, but really we're looking for that c value. So c equals 7/3. And I think that's it. Do we have any more questions? Final question. Let's go ahead and graph this graph. So we're looking for the graph of h. So again, I remind you, this is actually g, and this is g prime, right? So let's look at that. I actually think I have some stuff built in, so let's see. Yeah, so remember that this is the graph of g prime. So what we want to do is, I like to just fill out a very basic chart. And in order to do that, I have to know what are these values right here. What is interesting about this graph? Well, from 0 to 2, that sounds pretty good, but something happens here, so I'm going to include that something. So from 0 to 2, sorry, I keep saying that, -2 to 0, and then at 0, I'm going to put a point. From 0 to +2, and then at +2, I'm going to put a point, etc., etc. So what interested me? What are the points? Well, changes in slope, or here, changes in slope, so those corners, or x-intercepts were interesting to me. So I put all those in, -2 to 0, and then change in slope, 0 to 2, and then a root, etc., etc. So let's fill those out. The very first one that's easy for us to do is, again, we're trying to sketch the graph of g. So I just put g a bunch of times. I'm trying to sketch the graph of g. So what we're going to look at on the top is the relationship between G prime and G. We're going to look at on the bottom is the relationship between G double prime and G. So increasing, decreasing, and extrema, and concave up and down, right? So this is above the x-axis, so it's going to be increasing. Above the x-axis, still increasing, decreasing, decreasing, and increasing, right? So we know those. Increasing, decreasing, okay, good. We also can figure out our concavity, right? What kind of slope? Positive, negative slope, positive slope, positive. So it should go concave up, down, down, up, up. Let's see if we got that. Up, down, up. And it does say up behind this. It's hard to see. I don't know what this is and why it keeps showing up. Okay, I got it to disappear. There it goes. And then what we're going to look for is our critical values. So where's our critical values at? Right here. So at 2, we have a critical value, and at 8, we have a critical value. Okay, we have to test them, but we're not there yet. And finally, we actually want to look at our points of inflection. I should have put them down here because it's related to G prime, but I messed up and put it up here, sorry. So we have a change in slope here at 0, and we have a change in slope at 6. So we have possible points of inflection. Finally, let's test them. So testing critical values, I have to know that I'm going from my function is going from increasing to decreasing or decreasing to increasing. So here I'm going from above to below, below to above. So I can also test it here, increasing to decreasing, decreasing to increasing. So that's correct. That one's correct. Let's look at our points of inflection. We have to know our slopes are changing or concavity is changing. So concave up to concave down. Cool, that one's right. Concave down to concave up. That one's right. And then with our concavity, those are fine with our points of inflection. But with our critical values, we actually have to figure out if they're going to be relative maxes or relative mins. So I have a relative max at 2 because I went from above to below. So increasing to decreasing gives me a hill. From decreasing to increasing gives me a valley. So these are actually going to be a max and a min. And technically, we could also have seen if we had global extrema, absolute extrema, at our endpoints, like we could have figured that out. But right now, we're just going to work on this. So this tells me step by step what I can do. So increasing and concave up. Let's look at that. So here's my concave up. Which side's increasing? Not this side, this side. So this has to look like this. Then I have a change in concavity, so that's good. That means my concavity has to change. I have to go from concave up to concave down. I am. So this one's concave down, and it's still increasing. So it's this half, so this is going to be this half. Then I have a relative max at this point, so I have to make sure this is my max point. Then I am decreasing, but concave down, so concave down and decreasing. So now on this side, I'm doing this. Another change, so these must be changing. Good, we're good. So this says concave up and decreasing. So look at my concave up, that's this side. And then I have a min, and then I'm increasing in concave up. Okay. And then from there, I just do it on my graph. So what did I say? At 2, there was a max, so we'll just put it right here. And at 8, there was a min, so I'll just put it right here. So we went like this, like this. There's a change of inflection. Oh no, this is my max. There's a change of inflection right here at 6. Ooh, so it's gotta go like that, okay? There we go, and ta-da. So here I have a change of inflection, so here's my POI, and a change of inflection, so here's my POI, I did that correctly. Here's my max, didn't really work out. This should probably have come like that. That would be a more appropriate max. Sure, so let's just erase that. There we go, okay. There's my max, there's my min, and all my concavities and increasing, decreasing match up. So I was able to draw my graph of H, which is actually my graph of G. And I think that's our last question. Let's double check. Awesome. So that's it. We'll pick up on 7.7 next time.